Good morning. Hard to believe that we're already almost to November, but this next assignment that I'm going to collect is due in November. So things are really moving along quickly. What I can't wait for is Thanksgiving. We are starting on Chapter 5, and just to give you some context, the next exam that we're having covers Chapter 4, 5, and 6. And I think of those three chapters, Chapter 4 is probably the most difficult. In some ways, it's kind of like the apex of the course in terms of lots of ideas in one chapter. You know, because in Chapter 4, we were talking about rotational flow, Euler's equation, we were doing Bernoulli's equation, flow visualization, convective acceleration. You know, there's a lot of big ideas in there. Whereas here in Chapter 5, there's really only one idea in the entire chapter. We're going to spend 3 class periods talking about one relatively straightforward idea. It's an important one, which is why we talk about it a lot, and it has a lot of applications. But for the most part, it's pretty easy. So any questions related to the announcements before we get into the new material? All right. Let me dim the lights a little bit so you can see this picture. This is the Oahe Dam. The dam's at the bottom, and the Oahe Reservoir is upstream of it. And this is on the border of North and South Dakota. It's a very, very large reservoir, and it generates electricity, and it also helps to provide flood protection to the people who live on the banks of the river and farming communities where a lot of crops are grown in floodplains. And so it was built for, it was a multi-purpose project. It was partly to do flood protection, partly for electricity. It's owned and operated by the U.S. Army Corps of Engineers, and it's the 4th largest reservoir in the U.S. Artificial meaning that it's made by putting a dam onto a river. So we're going to talk a little bit about this dam as an example of the continuity approach and how you keep track of volumes. Here's a little bit of a zoomed-in view of the dam. And just to point out some of the features, the intake to the dam is here, where the water isn't taken right from the surface of the dam. It's an earth dam, and they generally will have the intake a little bit away from that, because if you have water going into a pipe, then it can cause localized high velocity, and then that could scour the material around the dam, which would be bad. You don't want the material from the dam going into the pipe, because the water's accelerating as it goes into the pipe and has some energy. And so they just sort of, they put a pipe into the water and suck the water out that way. Water flows through a submerged tunnel towards the power plant, and the vast majority of the time, that's how the water gets out of the reservoir. It's very uncommon for these release gates to be used. When the storms upstream in the watershed have gotten so high that they need to relieve some of the extra water out of the reservoir, then they'll open up these release gates. And so we're going to look at some video footage of when they opened up those release gates, just to give you an idea of the scale and how much water is actually coming out. So here's the power plant. And you'll notice, just if we go back to this picture, so the picture that we're looking at is taken from this bank towards this direction. Okay, so think about image analysis here. We're looking at the power plant towards the reservoir. The reservoir isn't very tall. This is not mountainous country that this was built at. And so you can get only a limited amount of electricity out of a dam like this, where it's relatively low head. And we're going to talk about electricity generation in Chapter 7, and we'll go into a lot of the details there. But one of the important criteria of how much electricity you can squeeze out of a reservoir is the height of the upstream elevation relative to the downstream elevation. And here maybe we've got, I don't know, 10 meters, 15 meters of head differential. So back in 2011, there was a series of heavy storms upstream of the dam, so in the watershed area that feeds into that reservoir. And because the water levels were rising so quickly, they had to send water through the overflow spillway. They're putting the maximum amount through the power plant, which is 50,000 cubic feet per second. This CFS is cubic feet per second. So they were maxing out the power plant, and then they were nearly maxing out the overflow as well, with 110,000 going through 6 of the 19-foot diameter spillway release gates. Now, just to put it in perspective, is 160,000 CFS a lot or a little? Maybe some of you are familiar with the Gauley River, right? That's pretty popular for whitewater rafting and recreation. So let me pull up the Army Corps of Engineers press release where they were announcing the schedule and flow rates for this season's Gauley release. Every September, they discharge water through the Gauley so that they can make room in the upstream reservoir for the winter flows. And what they were going to be doing during that period was 2,800. So, you know, I've been on the Gauley River during this season, and it seems like an incredible amount of water. You know, it's throwing you around like you're nothing in those little rafts. And, I mean, it's obviously a narrower river than the situation in Oahe, but 2,800 CFS versus, what we were talking here, 160,000. So this is a lot of water. Let's take a look at this water coming out of the release gates. Before we do the calculations, we'll sort of have dessert before we do the work, so to speak. So they sent a camera crew to document this historic discharge. And let me fast forward a little bit. You don't get necessarily a sense for how much energy is being dissipated quite yet. They have a zoomed in view here. These release gates are designed with scour in mind, because when the water's coming out, it comes out at a really high velocity, and it could threaten any non-armored concrete. They have to have a special high-strength concrete and are very careful about the reinforcing that they put on. Let's see here. So, I mean, the amount of energy coming out of these release gates is almost explosive. It's just got so much there. Let's see, there's another view that I like. Right. I don't know, when I see this now, you guys are seeing it through the horrible projector. It's a lot more clear and vivid on my screen, but it just makes me wonder what would happen if someone with, like, put on a life jacket and jumped in, you know? That'd be a wild ride, right? Maybe, maybe one that they wouldn't survive, but wild nonetheless. So look at all this water coming out. All right. So you get the idea, right? It's a lot of water. Message received? Okay. If you do it, I'll give your corpse extra credit. It could. I wouldn't know. All right. So here is looking at the water coming out of the pipes. And what did I say the diameter of those is? 19 feet. So think about 19 feet. That's taller than this room, right? And there's 6 of them? And the water's coming out that fast? Yikes, that's a lot of water. I think there was a picture. Oh, yeah, there's a guy standing over here. Does it show him? Or did it already show him? Anyways, okay. Yeah, there was a guy standing there. All right. So, there's an equation that I've showed you in lab, and I'm sure Dr. Ford has showed those of you who are in his lab section the same equation. You needed it when you were calculating the velocity in the, that tube where we were doing the flow visualization. You needed the velocity in order to calculate the Reynolds number. And so do you know what equation you used when you knew the flow rate, because you were quantifying that using the bench, and you knew the diameter of that tube, which gave you the area, So how did you find the velocity when you knew Q and A? V equals Q divided by A. This is a case where even if you forget the formula, you can kind of reinvent it by looking at the units. You know, we know that velocity should be meters per second, flow rate is cubic meters per second, area is square meters, and so it all works out the way we've written it here. All right, so it looked like a pretty high velocity in the picture that we were just, the video we were just watching. You know, we could have like thrown in something and watch it zip away and maybe try and like from frame to frame see how far it went. That'd be one way of quantifying the velocity, but let's do it this way. We know how much water is going through the power plant and how much is going through the gates. And so find the water velocity through the gates. There are a couple of hints that I could give you, but I'm not going to give you because I think that you'll probably figure it out without those hints. Well, let's take a look at the solution in just a minute, though. All right, so let's look at the solution here. So if the total flow rate is 110 CFS, then we have to find out how much of the flow is going through each one of those spillway pipes. So in the diagram that I put on the board here, it shows that it's 110,000 going into the spillway distributor, and then that flow is split between 6 different pipes. And we can make the assumption, I think, probably reasonably, that it's intended to evenly distribute the flow between all of them. So the flow rate through each spillway is going to be 18,333, and the diameter is 19 feet, which still doesn't make sense to me. When you see those pictures, they don't look like they're 19 feet, but I looked it up. They're 19 feet. Then we can get the cross-sectional area for it, and the velocity should be 64.7 feet per second. That's a really high velocity. You know, like think about if you jumped in, back to this again, right? If you jumped in and in 1 second you're going 64.7 feet per second squared, or feet per second. I mean, that's a really high acceleration, right? It probably wouldn't even take 1 second for you to reach that speed.
Like a hamster bubble?
Jump in a hamster bubble. Now that might work.
I don't see anything going on.
How many miles per hour? 44? Well, that doesn't seem so fast when you put it that way. Because people go water skiing 44 miles an hour, right? Yeah, you don't jump into it. All right. Any questions about the example? All right. So the equation that we can use, flow rate can be expressed 2 different ways, and the first of them is on a volumetric basis. The velocity that we just found is actually the average velocity inside of the pipe. It's not the specific velocity at a certain location in the pipe, and that may vary based on whether conditions are laminar versus turbulent, or where we are in the flow. You know, if we're at the edge of the pipe, close to the wall, then the resistance imparted by the frictional surface of that wall is going to slow down the velocity compared to the center of the pipe. So what we calculated was an average velocity, and here on the screen they're saying if you put a V bar over it, that's a way of emphasizing that it's an average velocity rather than velocity at a certain point. The diagram that's shown here is saying that if the velocity is known and a period of time that the water is flowing is known, then you end up with a volume of water, a certain quantity. And if the velocity is in terms of meters per second, for example, and you multiply that by a certain amount of time, then you can find out also with the cross-sectional area the flow rate, and an increment of time would give you a volume. So volumetric flow rate is one way to express it, and the other is mass flow rate. Volumetric flow rate, it works great if it's an incompressible fluid, like a liquid, because it'll allow us to say that there's conservation, and we'll talk about conservation in a moment. So You maybe have heard, like me say previously, that for a pipe, we've been talking about maybe convective acceleration, for example. I've given you the idea that if you have 1 liter of water that goes into the pipe, then a liter has to go out. And that's true as long as the fluid is incompressible. But if it's a gas, then volume isn't always conserved because the density of the fluid could change inside of some sort of apparatus. But what is always true is the idea of mass flow rate. And so if you have a kilogram of something going in, then over time, a kilogram has to come out. If you've reached equilibrium, then whatever mass comes in will also be coming out. So mass flow rate is just another way of expressing volumetric flow rate where we know, of course, that Q is V times A, so we can see that there. And then you multiply the unit weight in order to get units of kilograms per second for the mass flow rate. And so mass flow rate with m dot, if we reduce it down into volumetric flow rate times the density, then we get the mass flow rate. You'll use this equation a lot in Chapter 6 where we start talking about fluid momentum. And so mass flow rate isn't just sort of a one-time curiosity, but it'll be a very, very important part of the problem-solving approach for Chapter 6. Now, velocity isn't the same everywhere in a cross-section. What we just calculated in this example, the average velocity, works good when we're talking about turbulent flow, which is usually through pipes. But occasionally, we may have laminar flow. And what this picture is showing is a velocity distribution in 3 dimensions. And usually when I've shown it in the past, it's just been a 2-dimensional view where I drew the velocity profile similar to this, kind of a bullet shape, where at the center the velocity is high, at the edge the velocity is low, and when we go right down to where the velocity is in contact with the pipe wall, the velocity is 0. And so this is a parabolic velocity distribution, but now think in 3 dimensions. So this isn't just a 2-dimensional system. This is showing that in 3 dimensions you have a center where the velocity is going very quickly, and then all around the outside casing of the pipe, the velocity is reduced. And so one way to think of flow rate, Q, is to integrate tiny little elements across the area of a pipe and multiply the incremental area by the velocity for each one of these element areas. And so if we broke up this face that's shown here, the cross-sectional area, into tiny little pieces, then one way that we could find the flow rate Q is by integrating for each of those known areas the velocity multiplied by the size of the area. And we can do the same thing with mass flow rate, where we're just throwing the density in and multiplying the volumetric flow rate by the density of the fluid. And so mean velocity is saying that we want to know across the cross-section what's the average. And if you have a parabolic distribution like this, then it so happens that the mean velocity is half of the centerline velocity. The centerline is going to have the highest velocity because it's the furthest away from the outside edges. But if you were to find the average, in other words, the point at which half of the area is to the right of the line, half of the area under the curve is to the left, then it's half of the centerline velocity. But like I said before, most of the time conditions are turbulent. And this cross-sectional shape is more flat than the one above it when you have turbulent flow. And the dashed line represents kind of the average velocity over time. But then the solid line, which is waving back and forth, is showing the velocity at a single instant. So that if we took a glimpse of this same system an instant later, it maybe would have some different squiggles on either side of that dashed line, which is the average velocity profile. Okay, so let's take a look at another example that's using the idea of mass flow rate. This one is telling us that we have water flowing, no, not water, oil with a given density flowing through a pipe that's 50 centimeters in diameter, and we know the mass flow rate, m dot, is 550 kilograms per second. So based on that, what is the velocity, meaning the mean velocity, and the volumetric flow rate? All right, so we have the diameter in centimeters, and it's always really useful to write down the units of things in addition to the number, because if you accidentally used 50 instead of 0.5 when you're calculating the area, then the whole problem kind of falls apart from that. So I'd encourage you to continue, if you're doing the habit already of writing the units, then that'll make things easier for you spotting mistakes and understanding what the units of the answer are supposed to be. Okay, so we've got the mass flow rate, the density, and then here's our overarching equation here, that mass flow rate is density times volumetric flow rate. So we have the area using pi d squared divided by 4, and then rearranging this equation to solve for Q is what we get here. And the volumetric flow rate should be about 0.65 cubic meters per second. And then when we rearrange the volumetric flow rate equation in terms of velocity, we can get 3.30 meters per second for the flow velocity. Can you believe that the whole chapter is basically this idea over and over again? You're loving it, right? Yeah. It's a really important idea, the idea of continuity, where you're keeping track of volumes and keeping track of mass. It's something that comes up again and again, both in hydraulic engineering and in environmental engineering. And by the way, they just released the spring schedule online yesterday, right? And so I think most of you are going to be taking hydraulic engineering next semester. There's another possibility as well. And just recently, they changed the course hydrologic engineering to make it so that it could be taken concurrently with hydraulic engineering. Normally, what would happen is students would take fluid mechanics in the fall, then hydraulic engineering in the spring, and then the fall of the next year as an elective, if they wanted, then they could take the hydrologic engineering. Hydrologic engineering is kind of the study of watersheds, and in hydraulics next semester, we'll be designing pipe networks, and you always start with sort of a given flow rate. Q is given to you, the designer, and then you have to say how big the pipe should be based on that. Well, hydrology, which is this new class I'm talking about, gives you the flow rate Q. It looks at rainfall patterns, it looks at the size of watersheds and the type of land cover and the type of soil. And there are models for predicting what the runoff flow would be. So it's very relevant to the types of flooding that we had in West Virginia over the summer. Anyways, what I'm working up to telling you is that we're not sure whether or not the course would be offered this coming spring, because it's tough to predict the demand. And normally we offer it during the fall semester, but it's being considered as a possibility for the spring. So just based on the very brief information that I've given you so far, how many of you would have room in your schedule for hydrologic engineering and an interest in taking it? I think maybe the room in the schedule could be one of the issues. It counts as a technical elective. It's not a design elective. It's a technical elective. Yeah. So let's see. This is going to determine whether or not I try and press the department chair to offer it. Well, if it's my preference, it'd be a Tuesday, Thursday, but I really have no idea. Yeah. So I saw 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. That might be enough. I think normally it's 12. but there's also seniors potentially who haven't had it yet that could be interested. So I'll let you know. We're having a department meeting today, and I'll bring it up that there were 9 in here, plus whatever seniors may need it. So for those of you who don't take it next semester, I'd really encourage you to take it because it's a really interesting course. Hydrology has huge application, not only here in West Virginia, but all over the world. They're increasing storm intensities because of climate change, and flooding is becoming a big issue all over the place. All right, so any questions about this example? All right. The control volume approach is the idea of keeping track of fluids and where they are and where they're changing position over time. So what this is showing is a pipe that has a changing diameter and the flow has a changing direction. And so there's nothing special about this device other than just to emphasize to apply the control volume approach and the thinking behind it. The flow doesn't have to be uniform, and there are a couple of definitions that we need to take into account here. First of all, the system is the fluid itself, and so it may be a liquid or a gas, but by definition the system is a continually connected body of particles, and they can be moving or stationary. But the mass is constant because we define our system as a certain amount of water. What the control volume approach is used for is to keep track of where that water is over time. And so to do that, we first of all define a control volume, which is some sort of an enclosed space that the system may be contained within or flowing through. The control volume doesn't have to be stationary. The location of our control volume can be moving over time depending on what kind of a problem we have to solve. It can rotate, change position. And the outside area of the control volume is known as the control surface. And so it's just, the control surface would be the front face of how the water is entering the control volume here, how it exits at location 2, and then all the way around, usually conforming to the shape of the container, the outside edge of where the water is. So that's our control surface. And you'll notice that the abbreviations here, CV and CS, refer to both of those things. And I'll use those abbreviations in some illustrations here in a moment, and continuing on through Chapter 6 when we're talking about fluid momentum. So let's apply some of these ideas here. This is showing at a certain time that there is a fluid coming into a storage tank. And the fluid enters through the pipe on the left, and the fluid exits the tank through the pipe on the right. Now our system is just the dark blue liquid here. There happens to be some other liquid on in the inflowing pipe and the outflowing pipe. There's more liquid, but we've said that this is our system, the stuff that is pictured in dark blue. And so you'll notice that right now a certain amount of that fluid is inside of our control volume, and we've defined the control volume as the storage tank. You'll notice that the control surface is the outside edge of it, and right now the top of the control surface is the free surface at the top of that tank. It's defined here as a water surface, and so it's in open contact with the atmosphere. There also happens to be just a small fraction of our system is outside of the control volume. And they're defining that as the amount of mass that still has yet to come in to the control system. So this is all at time t. A little while later, at time t plus delta t, the location of the system has changed. You'll notice that that fraction of the system that was in the inflow pipe is now inside of the container, and some of the fluid is actually in the outflow pipe as well. Do you notice anything about the water surface between the two times? It looks a little bit lower. It's tough to notice because it's so subtle, but the liquid level is lower at time t plus delta t. So what does that tell us? what can we interpret from the fact that the liquid surface is lower? Okay, the water level is going down. There's more out than in. And so in the continuity approach, what we do is we keep track of where the water is to look at how any kind of fluid is accumulating in certain locations. And so the water that enters the tank can either be stored in the tank or it can exit. Those are the only two options here. The incoming water can flow out or it can be stored. And the system is unchanged. You know, this mass isn't going to be destroyed, it's just changing location. And the system is the number of particles that we've designated as our system. The location changes. Now, you can tell that if the liquid level went down, that's why there's more in the outflow pipe than there was here in the inflow pipe. It looks like, you know, this length, the amount of our system that's in the outflow pipe is larger than that little incremental amount that was in the inflow pipe still. So it sort of matches our expectations because the water level came down. So here are some equations. We could say that the system is at time t in the control volume and in the inflow pipe. There was a certain amount of mass in both of those two locations, and so the system overall is the sum of those two masses. At time t plus delta t, it's just in different locations. There is the mass that's in the tank, so it's the mass that's in the control volume. That's what this first component is. And then there's also a certain amount of liquid in the outflow pipe as well. The change between the two time periods, how much flow changed in the control volume, it's the difference between the inflows and the outflows. And so between these two time periods, during the delta t time increment, the amount of liquid in the control volume is lower. And so what that tells us, if the change in mass is negative, that means that the outflow has to be larger than the inflow. Another way of expressing that same idea is to say that the change in mass in the control volume with respect to time is the mass flow rate in minus the mass flow rate out. And so the mass flow rate out was larger, which means that over time the mass in the control volume is going to be decreasing. So it would be negative. All right. There's kind of just some interesting ideas that go along with talking about mass and where it is and the movement of fluids over time. Fluids can have both what are known as extensive properties and intensive properties. Some properties are related to how much there is, how much liquid there is. And so, for example, the mass of a liquid depends on, is an extensive property because it's proportional to how much mass there is. Momentum is the same way, where the, you know, those big jets of water we saw coming out of the Oahe Dam. The amount of momentum in that system depends on how much mass is coming through those pipes at any given time. So it's dependent on the mass. The color of the water, however, doesn't depend on how much mass there is coming out of the pipe. If we slowed down the flow going through those pipes to half the speed, the color would be the same. Although maybe it wouldn't look as turbulent, you know, we wouldn't see the white caps. The actual color of the water itself, if we took a sample and put it into a device that measures turbidity or color or viscosity, there are some properties that don't change as a function of the flow rate or how much mass there is. And so just to give you those definitions, because the text brings them up, some properties, like energy, it's common to talk about the energy in a fluid per unit mass. And if you normalize any one of these extensive properties based on a unit of mass, then that becomes intensive. So we don't end up using these definitions in much problem solving, but it's important to know when we get into the momentum chapter in chapter 6. Because when the fluid is moving, its properties are transported as well. And so a jet of water that comes out of a pipe, if it strikes something, then the energy that it had as it was moving is transported as the fluid is transported. And so the energy moves with the liquid. All right, so here's what we're going to do with the rest of the class time is a small in-class exercise. I am going to collect this one today and give you some homework points for it. This is looking at the Oahe Dam a little bit differently. It's looking at the volume of that reservoir that's there. The surface area of the lake, the average surface area, is 370,000 acres. And of course, the surface, let me dim the lights again. The surface area varies depending on the depth. You know, if the water levels are really low, then the river becomes narrow and the surface area of the lake is lower than if the water levels are high. And that's because, you know, if you think about, if we do a side view of a lake and what a lake looks like, usually lakes are like this. And so if the depth of the water is low, then the surface area is low. But then when the water level is higher, then the surface area increases. This value that I've given you of 370,000, for purposes of this problem, what we're going to assume is, just for simplicity, that the lake is, it has square edges to it. So that the area that's given of 370,000 acres is the average surface area. And also given in the problem statement here is the average depth of 63.5 feet. So you already know that in 2011 it was 160,000 CFS that was being released from the dam, and that's the combined flow through the overflow spillway and the power plant. So what I'm curious to find out is how long it would take to drain the lake. If we know how much water there is and the rate at which the water is being released. Now, when they had that peak flow rate that we were watching the video for, at that point the storms were mostly finished upstream of the reservoir, so there wasn't quite as much water coming in. There is a river that flows into the lake, and let's say that it's 40 feet wide, 8.5 feet deep, and then it has an average cross-sectional velocity of 3.5 feet per second. So that's one way that the water comes in. And then there's another upstream dam that's releasing 13 million pounds of water per minute. So there's one outflow, two inflows. What I'd like you to calculate, along with a classmate, is how long is it going to take to drain the lake? So you only need to turn in one of these. Be sure and put your name on both names on one of the papers. There's enough for everyone to have their own paper, and then after I score them today, I'll put them out in my box so you can collect them. There you go. If you prefer to work alone, of course, you're welcome to do that. All right, the little sketch is really important in this one, because once you've got the sketch, like the problem-solving process, I think, will just fall into place. You know, you've got a container of water, which is the reservoir, and you've got flow in and flow out, and we want to find out, I guess what I could have done is I could have drawn a little arrow to show that we know that it's draining. We just want to find out how long it takes till it drains. So if you know this strange conversion here, 43,560 square feet per acre, how many of you already had that memorized? Couple? Yeah. It's one that I've memorized, but I didn't always know it. Now I do. Now you will too. You'll always know it. So you find the surface area of the lake, and you know the depth of it, so that we're going to be able to get the volume. And we know the river flow rate in, and we need to convert that mass flow rate, pounds per minute, into cubic feet per second. So we have to know that it's 62.4 pounds per cubic foot, and then convert from per minute to per second. So I don't know why I'm showing you guys the answer if I'm going to be collecting this and giving you points, but I guess it's because I want you to know it more than I want to deny you points. All right, so any questions so far? Yeah, this is just a problem of in minus out. Out is bigger, so there's going to be a negative accumulation in the reservoir. And when I teach environmental engineering, the single most powerful equation I teach environmental engineering is accumulation is in minus out. You can solve so many problems with this idea. It's uncanny how many problems you can solve just by looking at what's coming into a system and what's going out of a system. All right, so we have the flow rates, and then accumulation is in minus out. I just look at the net flow rate out. Got to find the volume of the reservoir at some point, and then the time to drain it. Should be 76.3 days.
Did you memorize how many seconds
I had to double check. I thought it was that, but I'll admit I did double check before class. Yeah, so. All right. I did memorize how many seconds are in a minute. I've got that one down. Yeah. All right, so any questions, guys? All right, I want to give you some homework points for that, so be sure and give me your paper on the way out. I don't need to have everyone. If you've got 2 names on a paper, that's fine, but I'll give points to anyone whose name I see on one of these handouts. And so I will see you for more continuity equation on Thursday.